Okay, this is kind of an interesting one just in that we have this cubic on top, but it only has the x cubed in the x term. So I do notice right away that the degree of my numerator is larger than the degree of my denominator, so I'm suspecting that I'll probably have a slant asymptote. Before we jump into our long division, I'm going to work on my factoring, and then we'll see what we can get from long division. So I will factor an x out of the numerator, and I'm left with an x squared minus 4. The denominator is already linear, so there's not really any factoring to be done there. I can do a little bit better with the top. The x squared minus 4 is a difference of squares, so I can factor that into an x plus 2, x minus 2. And it looks like nothing is going to cancel, so I don't have any holes in the graph, but I do have zeros. And they are at, looking at the numerator for this, x equals 0 will make the entire fraction 0. X equals negative 2 will make the entire fraction 0. And x equals 2 will make the entire fraction 0. So there are 0, 0, negative 2, 0, and 2, 0. I do have a vertical asymptote as well. I do have this factor in the denominator that does not cancel out, and x equals 1 will make that denominator 0, which will give us that asymptotic behavior. That very, very small denominator when you're close to x equals 1 causes your y value to be very, very big when you're close to x equals 1. So it looks like I'm not going to be able to reduce before I do my long division, so let's just jump right in. We're dividing x minus 1 into x cubed, and I'm going to leave a space for the x squared, so 0x squared minus 4x, and I'm going to leave a space for that constant at the end as well. The first thing I need to do is make the x match up with the x cubed, so I'll need to multiply by an x squared. And I'm multiplying this entire thing by x squared, so I will get an x cubed minus x squared, and then I need to subtract to see what's left over. X cubed minus x cubed drops out. If it doesn't, you've done something wrong. 0x squared plus an x squared, be very careful with this sign, is just an x squared. And then we need two terms to work with because the thing that we're dividing by has two terms, this one right here. So we keep that 4x there just so that, again, things line up and it doesn't get confusing. I now need to make x match up with x squared, so I need to multiply by a single x. And that will give me x squared minus x. Again, we are multiplying x minus 1 by the x that we just tacked in there. And then we have to find out what our remainder is at this point, so we subtract. The x squareds drop out. Remember, this is actually negative 4x plus x when we distribute that minus through, so it's a negative 3x. And then you don't really have anything to drop down, but just to make things line up nicely, there's a plus 0 for our second term. Last thing we need here is to make the x match up with the negative 3x. Which means we need to multiply everything by negative 3, which will give us negative 3x plus 3. And when we subtract, the 3x's drop out, we get 0 minus 3 is negative 3. I don't know if I've made a big enough deal about this or not. The reason that I know to stop when I get here is as soon as the degree of what you're left with is smaller than the degree of your divisor, you're done. That's our goal, is to get down to a smaller degree than what we're dividing by. And for most of what you're going to be doing, that means you're trying to get down to just a constant. But technically, if we were dividing by an x squared, it would be okay to have x's in that remainder as well. We just need to make sure we end up with a reduced fraction. Okay, so I'm going to move this up here. This tells me that yet another form of my function r of x is x squared plus x minus 3. And then we have this negative 3 over x minus 1 tagged on at the end that didn't quite divide in evenly. The only thing we're using this form for is our global behavior. So we're thinking, okay, as X gets really, really big, positive or negative, what happens? And the most important thing is that because this is now a reduced fraction, 3 divided by a really big number, whether it's positive or negative, is tiny. So this is going to 0, which means as X gets really, really big, this dominates. This takes over. So I don't think I bug you to do many of these that get the quadratic global behavior, but I like to show one just so that you know this is also something that can happen. And I didn't pick one that ends up with a super nice quadratic that's not factorable. I can say that it's a parabola that opens up. We could do a lot of by hand work to figure out exactly what the graph looks like. For the purposes of this, where I just want you to see something kind of interesting, I think it's okay for us to just switch over and check it out in Desmos. So this is the graph of the parabola. You can see it crosses the y-axis at -3, and then it crosses the x-axis just past -2 and +1. So I'm going to roughly sketch that in and see if we can figure out what the rest of the rational function does. So we had an x-intercept just past 1 and just past -2. I'm trying to make those really little because this is the global behavior, not the actual function that I'm trying to sketch right now. And it crosses here. So just lightly sketching this in as like a dashed line. The vertex was just over from that y-intercept. So again, it doesn't really matter that there's this parabola in the middle. What really matters about this is that we're going to head up to positive infinity on both sides. It's just global behavior. It's just telling us where to put our final arrows as the graph leaves our window. We also had zeros, a lot of those. So actual zeros of our function at 0, at -2, and at +2. And a vertical asymptote at x equals 1. So we know that we need to come in near this asymptote, and the first piece of local behavior we hit is an x-intercept. Let's check our multiplicities. They were all 1, so we're not going to have any weird bouncing or mirroring on asymptotes. We then need to cross straight through, and the next piece of behavior that I need to worry about is the x-intercept at 0, 0. So we're going to turn around and come back up. That may dip down further, so you might even see it might cross. It's possible. I'm not that worried about getting perfect location of that minimum. That's going to be the job of technology for now, or calculus shortly. But I do want to see that you know where those intercepts are and that you should cross through. And then the next piece of local behavior is the vertical asymptote at x equals 1. So our options are either to continue up to positive infinity or to turn around to negative infinity. And since we do not have another x-intercept between 0, 0 and our asymptote, we'll choose the first option. We have to go up to positive infinity. So it almost looks like it's following that parabola shape really well. It won't necessarily match the parabola shape so well every time, but it is kind of an interesting one. Because this asymptote at x equals 1 had multiplicity 1, that means that if we went to positive infinity on the left, we'll need to head to negative infinity on the right. It has to change signs as you cross over that asymptote. And then we need to head up and hit our x-intercept and cross through. And then all that's left is that that kind of parabolic global behavior. So we're just going to head up here, and the graph is going to start getting closer and closer to that parabola. So it will keep moving out as we go, but it does get fairly steep. So not a vertical asymptote, but it is still increasing fairly rapidly.